minutes of the day. This is the fifth session on time response analysis. In this session, we will concentrate on steady state error and error constant. In the earlier sessions, we derived the expression for time response for a different type of input as well as different type of second order systems like underdamped, critically damped, overdamped and undamped, as well as different type of input like step, ramp and parabolic. Each of the response has two types. One is a transient and another one is a steady state. In the transient response, there are different parameters to measure like rise time, delay time, peak time, maximum overshoot as well as a settling time. These are the things we have studied in the earlier sessions. Now once it clears the transient response and it reaches the steady state response, what is the error between the desired output and the actual output? That is the steady state error. So in this session we will concentrate on steady state error and error coefficients. Now before going to the calculation of steady state errors, it depends on type number of the control system. Now what is the type number? Type number of the system is specified from open loop transfer function g of s h of s. So for the given system we need to find out product of g of s h of s, which is called as an open loop transfer function, and this type number is equal to total number of poles of loop transfer function lying at origin. So what do you mean by poles? Poles is obtained by equating denominator polynomial of the transfer function to 0. Roots of the equation of denominator polynomial equating to 0. So let us consider g of s h of s is something like k into numerator polynomial p of s and denominator polynomial q of s, where p of s and q of s something like s plus z1 into s plus z2 and so on the numerator polynomial, and s to the power n into s plus p1, s plus p2 and so on. Now here z1, z2, z3 are the zeros of the transfer function obtained by equating numerator polynomial, that is p of s equal to 0, and p1, p2, p3 as well as n times 0 are the poles. N times 0 because by equating denominator polynomial to 0 you will get a root as p1, p2 and roots n times it is 0. So p1, p2 and n times 0 are the poles of the transfer function obtained by q of s equal to 0. So here how many poles are at origin? N times. So n is the type number of the system. So for example, now in this 10 into s plus 1 into s plus 3 divided by s plus 2 into s plus 4, in this no poles are at origin, so it is the example for type 0 system. S is not present. So in this case 25 into s plus 1 into s plus 2 divided by s into s plus 3 into s plus 4, in this example only one pole is at origin, so it is a type 1 system. Whereas this one 10 into s plus 1 into s plus 10, whatever these poles, but we are interested in calculating this number of poles at origin. In this case it is 2, so it is a type 2 system. Now we will concentrate on steady state error. Now to find out the steady state error, first we need to get the expression of error. Now let us consider this block diagram where input is R of s, output is C of s, forward path transfer function G of s and H of s. So in this, suppose the error signal in the S domain. What is the error signal in the S domain? E of S. This E of S is the output of this summer, so which is equal to R of S minus C of S into H of S. This signal, which is the output of H of S, that means C of S into H of S. So if I substitute the expression for C of S, which is equal to E of S into G of S, the expression becomes E of S equal to R of S minus E of S, G of S, H of S. By rearranging E of S into 1 plus E of S, H of S equal to R of S, so E of S is this. So in S domain, error signal is equal to R of S divided by 1 plus G of S, H of S. Now, what is the error signal in time domain? That is E of t, which is the inverse Laplace transform of E of S. This is the general expression of error signal. General expression says this is a function of time. It deals with the transient response condition as well as steady state response condition. But we are concentrating only on steady state error, because in the transient state we have measured many things: peak time, rise time, overshoot and all. So what happens to the steady state error? Steady state error at steady state, ESS of t, is at t tends to infinity, limit as t tends to infinity, E of t. This is because steady state is obtained as t tends to infinity. And from the final value theorem, it is equal to limit as s tends to 0, s E of s. So ESS of t is equal to limit as s tends to 0, s into what is E of s? R of s by 1 plus G of s. So limit as s tends to 0, s R of s divided by 1 plus G of s, H of s. This is the steady state error. Now, steady state error when input is unit step signal. Now here, based on the input, what happens to the steady state error? Now we know that steady state error ESS of t is equal to limit as s tends to 0, s R of s divided by 1 plus G of s, H of s. When input is unit step, R of s equal to 1 by s. So if I substitute R of s equal to 1 by s here, what happens? This s and this s gets cancelled. So steady state error becomes limit as s tends to 0, 1 by 1 plus G of s, H of s. So this is 1, this is 1. These are the constant. If I apply the limit as s tends to 0, it will remains the same. So I can rearrange this limit function as 1 by 1 plus limit as s tends to 0, G of s, H of s, which is equal to 1 by 1 plus Kp. This I will consider as a constant, where Kp is position error constant, and which is equal to limit as s tends to 0, G of s, H of s. Now this steady state error is purely dependent on G of s, H of s. That is why in the previous slide we have concentrated on type number. Now what happens when the system is of type 0? Type 0 system, what happens to the Kp? It is something like s plus z1, s plus z2 divided by s plus p1, s plus p2 and so on, because no poles are at origin. As s tends to 0, what happens? z1 into z2 something divided by p1 into p2 something. So it is the constant. So this Kp, steady state error, becomes a constant. So what happens to steady state error? 1 by 1 plus Kp, which is also a constant. So type 0 system and unit step input, steady state error is constant, and error coefficient is also a constant. Now for type 1 system, what happens to the type 1 system? Kp is equal to limit as s tends to 0, s plus z1 into s plus z2 and so on, divided by s into s plus p1, s plus p2 and so on. So in this case, as s tends to 0, though these are the constant, but divided by 0, s equal to 0. So this steady state error constant, position error constant becomes infinity, hence steady state error becomes 0. Means it is matching with desired input. Output and inputs are equal. Now similarly, as the type number increases, here s becomes s square, s cube, s to the power 4 as the type 2, 3 and 4. In all the cases, the constant becomes infinity and steady state error is 0. Steady state error when input is unit ramp signal. Now once again, the expression for steady state error is ESS of t, which is equal to limit as s tends to 0, s r of s divided by 1 plus g of s h of s. Now when input is unit ramp, r of s is equal to 1 by s square. Now if I substitute r of s is equal to 1 by s square, what happens? This s and 1s gets cancelled, so it becomes steady state error as limit as s tends to 0, 1 by s into s plus s into g of s h of s. Now as s tends to 0, limit, this is one constant, this becomes 0 and limit as s tends to 0, s g of s h of s. So this will represent by kV, which is equal to a velocity error constant. This kV is, this is the kV is velocity error constant and limit as s tends to 0, s g of s h of s. So here is a slight mistake. So this is V. kV is velocity error constant. Now what happens for a different type of system? For type 0 system, kV is equal to limit as s tends to 0, s into g of s h of s, so s into g of s h of s. So if I substitute s equal to 0, it becomes 0. So kV is 0, hence steady state error, which is equal to 1 by kV, becomes infinity. For type 1 system, kV is equal to limit as s tends to 0. In the denominator s is there, this numerator s gets cancelled. This s and denominator s gets cancelled and expression becomes like this. And if I substitute s equal to 0, it is a constant. Hence steady state error is also a constant. So type 2 system, it is g of s h of s has two zeros at origin. So 1 by s square into something, so ss gets cancelled. So s plus z1, s plus z2 divided by s into this. So in this case, if I substitute s equal to 0, it becomes infinity, hence steady state error is 0. So as the order type increases, steady state error constant is infinity and steady state error becomes 0. Now we will concentrate on steady state error when input is unit parabolic signal. Now as earlier, steady state error ESS of t is equal to limit as s tends to 0, s r of s divided by 1 plus g of s h of s. Now when the input is unit parabolic input, then r of s is 1 by s cube. So for unit parabolic signal, r of s is 1 by s cube. If I substitute r of s 1 by s cube in this expression, it remains 1 by s square. So ESS of t becomes limit as s tends to 0, s square plus s square g of s h of s. So if I apply limit to this, 1 remains the same and s square becomes 0. So limit as s square g of s will remain. So this is because this s square, by substituting s equal to 0, becomes 0, but we don't know what is g of s h of s. So that is why we are retaining this as it is, and which is equal to 1 by Ka, where Ka is an acceleration error constant. So when which is equal to limit as s tends to 0, s square g of s h of s. Now we will see one by one for type number of the system. Now for type 0 system, limit as Ka is equal to limit as s tends to 0, s square. This is the s square, and this is type 0 system. So when I substitute limit as s tends to 0, it becomes 0, hence the steady state error is infinity. Means there is a large gap between desired output and actual output. Now for type 1 system, which is having one pole at origin, so Ka becomes limit as s tends to 0, s square and one s in the denominator gets cancelled, and so becomes s into s plus z1 plus s plus z2 and so on. So limit as s tends to 0, this because of this s in the numerator, it becomes 0, and steady state error is infinity. Now for type 2 system, Ka is equal to limit as s tends to 0. Type 2 system has one s square in the denominator. So this s is not there. So it is s plus z1 into s plus z2 into s plus z3 and so on. So this is a constant. So Ka is a constant, hence S of t is also a constant. Now overall summary. So this is the type of the system and this is the type of the input. For unit step and step 0, both steady state error constant and steady state error are the constants. For type 1 system, unit step input, positional error constant is infinity and steady state error is 0. As I mentioned, this is the type 0 and unit step, only it is a constant. For higher orders, it is steady state error is 0. Now for unit ramp input, type 0 is having high steady state error, that is infinity, whereas type 1 system will have constant steady state error, and type 2 onwards it becomes a 0. For unit parabolic, for lower order, lower time system, type 0 and type 1, steady state error is infinity, and for type 2 system it is a constant. So based on this, we need to calculate what are the constants and steady state error based on the type of the system and type of the input. For some, it is a fixed one. Steady state error is either 0 or either infinity. But for these diagonal elements, type 0 unit step, type 1 ramp, type 2 and parabolic input, it is constant. So constant value we need to calculate. That we'll see in the next session. Thank you.